Let me share this out so you guys can see it a little bit better. Let me also make sure that I'm recording. All right. So first, a few things about just Lisp in general. We discussed the idea of the traditional IP addressing and what that does for us in IPv4 or in IPv6 for that matter. The concept is the idea that our IP address really denotes two separate things. Who we are as an endpoint, right? Identifying the individual host, and then where are we physically located? We're going to route based off of that destination IP address. So we're going to look for how do I have a route to get to that destination address. Well, Lisp, its whole idea is to separate those two functions. We have an IP address for your host identity. Who are you? And then we have an IP address for where are you physically located. What router are you connected to is what we're really looking for in this case. And in an SD access environment, you can think of your entire fabric environment as all a routed environment. It's like having layer 3 at the access layer of our hierarchy that we're utilizing within here. So the idea within Lisp is that we're going to have a few different devices. First off, we mentioned why we want to use it. Well, it's flexible addressing. It allows for the assignment of multi-homing. It gives us provider independence. It allows for mobility and virtualization. And we started using a lot of Lisp when we start dealing with the idea of data center environments. You start seeing a lot in an IPv6 environment where we have to recognize where we're going through and being able to do tunneling from IPv6 to IPv4 and back to IPv6. So there are many different ways that we have or reasons for why using Lisp. Okay? Now, in an SD access environment, the whole strategy that we're utilizing this locator ID separation protocol is to say we want to be able to extend VLAN information from one routed access layer switch to another routed access layer switch, and potentially out to another location across a WAN environment if we wanted to. Okay? I don't know why you'd want to, but you could do that. Now, in an environment like a data center, Lisp allows for us to be able to take a virtual machine from one data center, move it to another data center, migrate that to a different data center, and allow it to still use the same IP address, subnet mask, default gateway. It doesn't have to flesh out its ARP cache by any means whatsoever. And the idea is now we need to find out where is that IP address located. Okay? So we're going to see that Lisp also offers an alternative to the traditional network architecture by introducing these two separate addressing spaces, two completely separate IP addresses. We have one that indicates where are we located, what they call the router location. Which router are we connected to? And this is used to route all that traffic through the underlay network in our SD access environment. And then we have the endpoint ID that we're dealing with there, the endpoint identifier, which is used to specify the device itself that we're communicating with. Right? So as we want to talk to an individual server, or in this case, even an individual user, the whole idea is that to reach that endpoint, I've got to get to this destination router. So let's give kind of an example here. I'm going to draw some things up on the board and kind of equate what we've got in Lisp versus what they're going to call it in DNA Center in an SD access type of environment. And as a matter of fact, I think I've got one more slide I think I want to show you. Oh, there you go. Some of the components of Lisp. We mentioned that we have the endpoint ID, which is the host IP address, the router locator, which is the routers that those endpoints are connected to. Lisp uses this concept of a tunnel router. There's both an ingress tunnel router and an egress tunnel router. And it kind of depends on how the data flows. Right? So as it comes in from some device that is not Lisp compatible, a non-Lisp site, you're going to see the first router it hits in the Lisp environment is known as our ingress tunnel router. It has to do a lookup to what we call a map resolver in Lisp, saying, how do I reach this IP address? That map resolver will send back a router location. That IP address is at this destination router. And we'll put on an extra IP header on that information to send it to the correct egress tunnel router. When it reaches that egress tunnel router, they'll strip off the external header, and we'd be left with just the endpoint identifier, and I will deliver it correctly to the right end host that we're looking for. Okay? So important to recognize some of these LISP ingress and egress tunnel routers. If it's on a device that is connected outbound, that's not a part of the LISP environment, make sure that this actually works here. You will see they call them a proxy XTR, okay? And again, the XTR is just the idea that it can do both ingress and egress tunnel routing that we're looking for, okay? The proxy tunnel router is essentially to say, hey, this host is not a part of the LISP environment, but we need to know how to reach that host. So these proxy ingress tunnel routers will go through whenever we receive someone that's not a part of the fabric, we'll then send that information. To get to that IP address, you need to reach this tunnel router. And I'll send that information to what we call our map server. And our map server is essentially nothing more than a database. To get to this IP address, go to this router location. Okay? Typically, you will see that the map server and the map resolver reside on the same host. It doesn't have to, but they can. And we're going to see within here a couple different things. These proxy ingress and egress tunnel routers that we're dealing with, those in DNA Center are known as a border node. So when you go through and set it up in DNA Center, you have to configure one of your switches as a border node. It's connected to some site that is not necessarily a part of this SD access environment, right? Outside of the LISP environment is what we're looking for. Then we have the regular ingress and egress tunnel routers. These guys right here are known as, in DNA Center, as edge nodes. And they would be connected to your servers or your users in an SD access environment, right? Typically more users in this environment than the servers that we have. Our map resolver, map server, is also known as, in DNA Center, a control plane node. And you'll see when we go through and set up DNA Center, we can configure a device as being multiple things. It could be a control plane node where it runs the map server and map resolver and keeps that database of all the different endpoints and which router location are they at. And it may also be a border node device as well, connecting outbound to some location that is not a part of the SD access fabric that we look for. Okay? Then the edge nodes would be typically where you would see our access layer switches in a traditional hierarchical network in Cisco. And so these edge nodes are the ones that are talking to our hosts that are a part of that SD access environment. Okay? Connected to those hosts. And so when we look into this environment of LISP, we can think of something like this. I'm going to go through and create some site that's out over here. I'm going to call it non-LISP site. Okay? As it comes in, we will see that we typically have at least 2 distribution layer switches in a normal environment. These may also be core layer switches right over here. These guys are typically both a control plane and a border plane node within inside DNA Center. Okay, so this would be a control plane and a border plane node. Now, the idea being is that if your control plane node, you're running the map server, map resolver in LISP. You may only have one of those. Okay, you may not see both of these guys being a control plane node. 2 of them adds to redundancy. In case this device fails, I've got another device that can support the idea of being that map server, map resolver. They're both border plane nodes because they've got a connection that goes outbound towards these sites where we're not using any of the SD access, right? Normal destination-based routing, a regular network, whatever you want to call that. Okay? And then they also have interfaces that get connected down to our access layer switches, which are also known as edge nodes. And again, usually you're going to see that these guys are dual home that are out over here. And then we would have our individual users that hang off of these access layer switches. Okay. Now, one of the beauties that we're going to see within here is that when we have an edge node, let me give you an IP address. I'll put this in black. A user gets assigned an IP address 10.1.1.1. Okay? What you're going to see happening as they connect to the access layer switch, we're usually going to have some type of authentication for that. A lot of times using 802.1x, but might also be using digital certificates to recognize who that user is. Now, this is where you start seeing that Cisco DNA Center and the integrated services engine or security engine that we have is going to be tightly integrated between the two. So DNA Center and ICE are going to have a really tight relationship. If you know much about ICE, they're using the PX grid services within ICE, which is to allow for third-party interaction to our security node. And DNA Center uses that regular PX grid services, like any other vendor would have to do, to integrate within ICE. The idea is that as the user connects, I can authenticate that user, find out who they are. Now that I know who they are, what subnet should I assign that user to? Okay? And what VXLAN is this interface going to be a part of? We'll discuss VXLANs later on in another tech talk. The edge node, in this case, is going to have an IP address. And I'll write all the IP addresses of our devices out over here. I'm going to call this a 192.168.1.1, and this a 192.168.1.2. I'll make this one a 192.168.1.3 and a 192.168.1.4, just to make it easy. Okay. In DNA Center, these IP addresses that are in red right here would be what we call our underlay network. How do we get from one router to another router? And we've got ISIS routing that tells us what's the best path to get from any one router to any other destination router. Remember, this is all a routed infrastructure here, okay? So there is no switching involved, meaning no spanning tree that we have to worry about, no interfaces shut down due to that spanning tree protocol. If I add in another link, have another border plane mode out over here, I can connect all of our access layer switches and they just simply load balance. I got multiple paths to get to the exact same destination network, so it adds to redundancy on that environment. What happens here is that when that node, the end host, gets an IP address, the access layer switch then sends information to the control plane node. I have an end host, 10.1.1.1, just to connect it to my access layer switch out over here. They're at the router location of 192.168.1.1. So the control plane now knows if we ever receive inbound traffic from this non-LISP site that has to go to this destination IP address, we have to send it to that particular router. Now, likewise, you'll have the same kind of concept. I might have another user out over here that gets connected to the same VXLAN between these two access layer switches here. So let's say that they're given an IP address 10.1.1.2. And again, as soon as they get that IP address, that edge node device goes through and contacts the control plane, saying if you need to reach the 10.1.1.2 address, they're at a new router location. In this case, it's going to be a 192.168.1.4. Now, we may have traffic that has to go from this node to this node out over here in the same subnet, essentially. But again, remember that all of this in between is a routed environment. Normally, you can't route from one IP address to another IP address on the same subnet through multiple interfaces. But this is how that LISP gets that done. We're going to take a frame. Let's say that that frame has got a source IP address of, and I'll make this in black since they're going to be end hosts, excuse me, So the source IP address is 10.1.1.1. The destination IP address is going to be 10.1.1.2. Right, so we're talking about traffic going from one node to the other node. As that packet comes into the access layer switch, it has to do a lookup to the control plane node, our mapped resolver. It says, how do I reach the destination address of 10.1.1.2? And it's going to say, to get to that IP address, you need to reach this router location. So what they're going to do is encapsulate this internal packet right here with a new IP header. I'm going to write it right here. I'm going to erase just a little bit right here just so that we can see what's going on. And then that new IP header, they now have another source and destination address. Our source IP address would be a 192.168.1.1. And our destination address would be the other router that we're looking for. I'm trying to make this a little bit smaller. Would be a 192.168.1.4 in this case. So as it goes through the routed environment, it's going from this access layer switch to the other access layer switch. As it comes up to this distribution layer switch, it's just simply routing on the external header. How do I reach 192.168.1.4? And I've got a route to reach that. It says go in this direction to get to that router. Once we've reached that destination, that edge node device says, yep, you've gotten to the right router location here. And it's going to then go through and strip off that layer 3 header, that external header, and look at the internal IP header that we have available for us. And in the internal header, it says it's destined for a 10.1.1.2, which it knows is on this interface, and it sends it out onto the other link. So Lisp is used to register those endpoint IDs to the control plane node. It's also used to do almost like a DNS lookup. It asks information about how do we get to the destination host IP address. And that will then send us a router location for that particular host. Okay? That allows us to then put an external IP header on it to send it through this routed environment to get to that individual host. Now it seems like I've had some questions here, so hang on a second. Let me answer some questions. I've got in chat. Thanks, Russell. I'm going to jump out. Okay, no problems. Derek, I'm hoping that you got all of your audio figured out. Are you okay? Okay, that's no problem. So if you don't have a mic, it's no big issues. If you have any questions, please feel free to ask them in chat though, okay, Derek? And that goes for you as well, Dario. You need to just feel free to send me a chat message, or if you've got, I'm pretty sure you have audio, so if you have audio, you can just ask it as well. Now, when we deal with the locator ID separation protocol in the SD access environment, all it's really doing is to say, how do we get from one node to another node? Okay, so that's the important part that you're looking for up over here. Now, we may also see traffic come in from this non-Lisp site out over here. Let's make it green in this case. And so packet comes inbound, and it's got a source IP address. Again, I'll make that right here, source IP. We'll make it 63.1.1.1, like it came in from the internet. And it is destined for a node, destination IP, we'll call it 10.1.1.1. As it comes into the border plane node, or the border node that we have up over here, which is really also known as a proxy ingress and egress tunnel router in Lisp. That border plane node asks the control plane node, how do I reach 10.1.1.1? And it says, oh, you've got to reach this particular router. It also goes through and automatically registers the source IP address of this packet. Hey, if you ever receive information and it's destined for a 63.1.1.1 address, you need to send that information to my router ID, which is a 192.168.1.2 address. This original packet then, again, gets encapsulated in a new IP header, where our source IP address, again, let me make this just a little bit smaller so that I can And our source IP here is going to be the control plane, which is a 192.168.1.2, and our destination IP address of that packet will be the router node on the other end, 192.168.1.1. And that delivers that packet. Again, takes that information, once it's in the border plane is looking at the external header. How do I reach a 192.168.1.1 address? And it sends that information out onto that edge router. That edge router receives that saying, I am that destination address, so it would strip off the external header to look at the internal header. How do I get that to a 10.1.1.1 address? And again, I would deliver that original packet out onto that host, knowing where they're at based off of their authentication and what we saw within ICE. As traffic goes back in the other direction, this access layer switch has no idea how to reach 63.1.1.1. So again, it does a lookup to the control plane. How do I get to 63.1.1.1? And it says you need to encapsulate that and send it to a 192.168.1.2. So I put in a new packet header on there, send it out onto this control plane node at 192.168.1.2. They will then again strip off the external header and send it to the internal header. All right, well, how do I reach 63.1.1? And it's going to go out in this direction. Okay. So the whole idea within Lisp is to say that to get to an individual edge point that we have or endpoint that we have, you need to know what router is it connected to so that I can deliver it correctly across what we call our underlay network. That then works hand in hand with VXLANs on how do we actually take VLAN information. Normally, to extend a VLAN from one access layer switch to another access layer switch, we need trunking, 802.1q involved within here. VXLANs allow us to take that packet and encapsulate it with a new IP header so it can go sent through a layer 3 cloud. I'm essentially expanding that VLAN between different devices that are through a routed network in the core. Okay? So that's what we're seeing between the idea of Lisp and VXLANs. Okay? Now we're going to talk a lot more about VXLANs in my next tech talk that we go through, so I hope you guys can join back in later on as well. Now they go through and they kind of show a picture of this on my slide here. So I've got my data centers in this case out over here. Got my tunnel routers. These would be my proxy tunnel router up here at the top. And this is all of our Lisp site that we're utilizing within here. Notice we have this host 10.4.4.44 is in some other network and not a part of the Lisp environment. And that's why I would tell you that this top router is known as a proxy ingress tunnel router right here. Or a border plane node in SD access. These guys are both an ingress and egress tunnel router, but they're part of the Lisp site. So these are typically what we would call our edge devices in an SD access environment. So we might see, and we might start off this entire thing. Oops, hang on a second, I think we actually do. I'm going to slide as one step forward here. So we start off right over here. My host, 10.3.3.101, is at this data center. Notice that my ingress tunnel router connects to the map server that we have out over here and says, hey, to reach a 10.3.3.101 out over here, you need to reach my IP address. So they've got to get to 10.3.3.101, you need to get to my IP address of 192.168.13.2 at this point. As that host moves, again, in this case, we're looking at a virtual machine, but it could be any host moving from access layer device to access layer device. Think your users as they move from a wireless access point to wireless access point. They may change where they're connected to on the wired network. As soon as I move and I communicate with this ingress and egress tunnel router, it makes an update to the map server, map resolver. 10.3.3.101 is now at a new router location, and they send them the IP address of 192.168.23.2. So you got to advertise that and send that information out onto a 192.168.23.2 at this point. When traffic comes in from 10.4.4.44 up here at the top, it has a packet header, and I'm going to write this right here, again, so we can kind of see this information, with a source IP address of 10.4.4.44. And it's got a destination IP address of a 10.3.3.101 in that packet header. As it comes into my proxy ingress tunnel router, it does a lookup to the map resolver. Hey, where is 10.3.3.101 at this point in time? And the map resolver looks into its database and says, at this point, it is located at the router location of 192.168.23.2. My proxy ingress tunnel router is going to add in a new IP header on the outside of this information. It'll be a source IP address of the proxy ingress tunnel router, in this case a 192.168.214.1. Its destination IP address that it puts in this external header will be a 192.168.23.2. As it gets sent through this environment, through our LISP environment, it's just simply routing on this external header. How do I get to a 192.168.23.2? Well, my best route is to go through this next hop router. This guy would typically be just a distribution layer switch that you might potentially have, or distribution layer router that we're looking for here. So it's not an end node, they call it an intermediate node in SD access. Simply looking at this destination IP header in the external header. And it says, yeah, I know how to get there. I've got a route to be able to reach that destination router. And it sends it outbound to the correct egress tunnel router. When it reaches the egress tunnel router, it says, you've reached your destination. That means I need to process this packet. So it strips off that IP header and looks at the internal IP header. How do I reach the IP address of 10.3.3.101? Well, that's connected out to this interface, and I send it out onto that individual user. Okay. And likewise, that traffic going back outbound. Remember that as this guy is a proxy ingress tunnel router, he has also gone through and said, to reach the 10.4.4.0 subnet that we have out over here, you've got to go through a 192.168.214.1 address. So as my host, 10.3.3.101, wants to send traffic back to 10.4.4.44, again, it builds a packet with this as a source IP address, 10.4.4.44. It's going to be the destination address. As it comes into the ingress tunnel router down here on the bottom, it does a lookup. How do I reach the 10.4.4.0 subnet? I've got to send it to a 192.168.214.1 address. I'm going to re-encapsulate it with a new IP address and route that outbound to the proxy tunnel router, who would then strip off that external header and deliver it correctly outbound to the 10.4.44 address. Right? Just simply routing. What's my best path to reach the 10.4.4.0 subnet? Do you have any questions on that?
Yeah, just a quick question over there. Do we have over here the concept of Anycast gateway as well, or the access, like the SD access are going to be the default gateway for the host, or how will that work over here?
Yeah, so essentially, as these hosts, they're in the 10.3.3 network, every one of these edge devices acts as if it is the default gateway for that subnet. Okay. So they essentially have, think of it like an Anycast address that they've got. Let's make that default gateway for all these users a 10.3.3.254, for instance. Right? Both of these two edge routers answer to that IP address, kind of similar to like HSRP, if you will, with these devices never sending hello messages back and forth between each other. Okay? They're both active devices that can be used as the default gateway. And that way, as my 10.3.3 host is out over here, it still can get to its default gateway. As I migrate that to a new location, it can still get to its default gateway.
Okay, perfect. Yeah, so it's basically the same Anycast gateway concept of what we have with normal VXLAN, correct?
Absolutely. Yep.
What about like you mentioned right now that every time that, for example, the server 10.3.3.3 needs to communicate with the computer, it's going to do a lookup to the master server. Is that lookup every time that it's going to send a packet, or is it going to have any caching algorithm over there that is going to hold the router location for some time?
Yeah, so they cache that information for a total of 1 minute, so just 60 seconds. So anything past 60 seconds, I gotta need to do another lookup. Whenever there's a change to the database, so if someone ever makes a change to this database, the map server tells everybody about that. Hey, there's been a change to the database, so flush out what you've got for a cache.
Okay, and that minute is going to expire every minute, or that's going to be once you reach out a minute without sending traffic?
Yes, so it would be a 1 minute of inactivity. If I don't see any traffic going to that individual host, I'll flush it out of my cache. But if traffic keeps on going to that host, keep it in my cache over and over and over again. Unless that map server tells me there's new information in the database. Okay, in which case I would flush my cache and make another request. How do I get to the 10.4.4 address? Right, and that would be particularly useful if you had something like this. Let's say we don't have just one proxy ingress tunnel router out over here. I might have two of these proxy ingress tunnel routers out over here. What happens if, by default, I was sending everything through this router and then this router failed? Well, the 10.4.44 network is now going to be updated and say, hey, by the way, now you can go to this other router. The map server is going to say, flush your cache. And the very next packet, I'm going to say, what's the new router location for it? Oh, okay, and I can send it through the new router location.
I got you. On that case that you have two routers over there, how would you do the redistribution, or not the redistribution, the advertising between the LISP subnets and the non-LISP subnets? Are you going to advertise it, both routers out of the other domain, or how will that work?
So you'll see it happen like this. By default, they'll have in this router location that the same subnet, 10.4.4.0, can be reached via a 192.168.214.1 and a 192.168.214.2 address, let's say. Okay, the two routers that we have up here at the top. Now, as traffic starts to go from that 10.4.4 network, I receive specifically 10.4.4.44 sending traffic up onto this host 10.3.3.101. What you're going to see happening, notice how these guys have a /32 for a route to reach this individual host. You'll see that eventually happening through in this case as well. To get to 10.4.4.44, your best route is a 192.168.214.1. Go through that one single router. But again, if that host should fail, we're going to see I don't have information on how to reach that network. And that's going to be ISIS that tells us about that. Right? All of these routers in this environment are dealing with ISIS. And so when that router fails, it says at the map server map resolver, flush any routes that go to that router ID. So it throws out this route. Well, now the only other route that we would have, if I flushed out that guy, the only other route I have to reach that 10.4.4 network is through a 192.168.214.2. So now I send it through the other router at this point. Okay? So yeah, that gets flushed immediately when we see a change in ISIS. I lost connectivity to this router, so dump all the information that we have that has to send traffic to that router. Hopefully, we will find then another path to get to that same destination network. Now, as soon as that traffic starts to pass through the new router, they will go through and make an update to reach a 10.4.44.44 with a /32, go to a 192.168.214.2 address now. Okay, so we have more specific information about that one individual host at this point. Does that answer your question?
Yeah, so the first packet is going to be, for example, if the traffic, instead of flowing between 10.4.44, the first packet is going to take pretty much a equal cost multipath, whatever, and it's going to just flow through one router, but then the return traffic could just like go through the other router, and that's where all the path is going to update, right?
Absolutely.
Okay. Thank you.
Yeah, you're welcome. So again, one of the big points about it, as far as I'm concerned, is what do they call it in Lisp versus what is it called in DNA Center for the SD access environment, okay? So remember, we have things like in Lisp, they would call this a proxy ingress and egress tunnel router, where DNA Center calls that a border node. Lisp would call this just a regular XTR, where again, DNA Center would call these edge nodes that we have out over here. These are just Lisp routers. They're not connected to any users or any outside network. Right? So all they're doing is just simply forwarding on that external header, IP header that we have. And how do we get from one router to another router? DNA Center would call these intermediate nodes that we're dealing with at this point. The IP addresses of all the routers. DNA Center they would call that the underlay network. The IP addresses of our hosts, like this 10.3.3.101 address, that would be known as an overlay network or a virtual network that they create in DNA Center. Okay? So it's really kind of important because you're taking multiple concepts, Lisp, VXLANs, and then how is that used in an XC access environment that are named different things depending on what it is you're actually talking about. Okay? Important to kind of correlate all of those names that they use for that stuff as well when you're dealing with configuring DNA Center. Any other questions for you guys? All right, that's pretty much all I have for you guys when it comes to Lisp in the SD access environment. So hopefully you guys can come back in a couple hours and we'll discuss the idea of how the VXLANs are then involved within that process. Okay.
Quick question: are you going to have like the afternoon meeting? Are you going to have that on another time or date? Because I've overbooked for that. I would really like to join, but like I don't know if you have another times that you're going to have that.
Sure.
meeting.
Hang on one second. I've got a couple different things here, so I'll make sure I know, because we're going to have it a couple days. They sent me what my schedule is here. Oops, hang on. Yeah, so the VXLANs are going to be from 1 o'clock to 2 o'clock today. But we're also going to record it, just to let you know, okay? I'm recording this session as well. So if there's something that you can't meet that, and apparently that's going to be the only one for this week. So if you can't come to that, look into the idea, are you a next, SLI Next customer at all?
I'm not quite sure. We are a partner from you guys, but I'm not quite sure.
So do me a favor. And let me find her email address real quick as well. Oh no, do that. You can send an email. Hang on, let me find out where that is. It should be, oh, I'll write it so that's easier to see. E. McCann? McMahon? And check to see if you'll have access to be able to get to that for that recording, okay? If not, I know I'll probably do another one of these as well. So when that's going to be, I'm not quite sure.
Perfect. Awesome.
Okay.
Thank you, sir.
Yeah, you're welcome. And hopefully maybe you can make it back later on today. It's only another hour, so who knows?
I wish. I have a meeting that I had to attend.
Okay. But other than that, that's all I've got for you for this particular talk. Looks like I've also got another chat. Let me ask this one. And Dario, I think I already got that, but I'm going to keep your email address. If I can find anything that I can send you, I'll let you know, okay?
Perfect. Thank you. Have a
You're
good one,
welcome.
sir.
You too.
Bye-bye.
Derek, the same goes to you as well. So hopefully you're going to be back at our VXLANs. If not, thanks for showing up.